And welcome to algebra. We'll be talking about the corollary 6.2 unique factorization domain divisibility. Now, the claim is that let R be an integral domain. Then 1. For each AB from the underlying set of the integral domain, there exists the greatest common divisor of both elements. Number 2. Every irreducible element is a prime element. And number 3, we have that there doesn't exist a sequence, an infinite sequence of elements from the underlying set, or rather I can simply write like so, such that for every I, the element AI plus 1 divides the element AI, and such that AI plus 1 is not associated with AI, meaning you cannot obtain it by multiplying it by an invertible element. An example of such a sequence would be, say, 8, 4, 2, 1, 16. In this notation, 16 would be A1, 8 A2, 4 A3, 2 A4, and 5 1 A5. Now, here it's obvious that this sequence must always be finite, because we begin with the biggest, and we then start going down, right? We have a decreasing sequence, which is, however, greater than 0. But not so obvious for general integral domains. That's what we'll prove. Now, onto the proof. So proof, and shall first prove the point number 1. Alright. Let Pi, there's some sequence of Pi's where I ranges through 1 to n, be such irreducible elements from the underlying set of the integral domain, such that, and we have A is associated with P1 to K1 ... to Pn to Kn, and B is associated with P1 to L1 to, times ... all the way to Pn to Ln. Right, so essentially we take these prime factor decompositions, these factorizations of irreducible elements. Now we want to prove that A and B have a greatest common divisor. Alright. Oh, I should also point out that it could easily happen that A and B do not share the same factors, but that's okay, because if they don't, if there is some factor that A has that, say, B doesn't, then we include it in the decomposition or factorization of B, but we simply raise it to the power of 0, right? So its associated L would be 0. The converse is also true. Now put C equal to P1 to, say, M1 times P2 to M2, and continue all the way to Pn Mn, where for all I, m is a non-negative integer smaller than the smaller of the two corresponding exponents ki and li. Now this gives us the set of all common divisors of A and B. Because if there was even one P whose exponent wouldn't follow this rule, then it would automatically fail to divide at least one of them, at least either A or B. Therefore, all such C's form the set of all common divisors. And therefore we put the greatest common divisor of A and B equal to the greatest possible value for individual mi's, that is P1 to the minimum of K1 L1 times P2 raised to the power of the minimum of K2 L2 all the way to Pn raised to the power of the minimum of Kn Ln. Right, so we have, and this satisfies the definition of the greatest common divisor. One, because it is a divisor, because we took it from the set of all divisors, and secondly, it is the greatest because if even one exponent was even bigger by 1, it would automatically fail to divide at least one of them from these decompositions that we have here. I believe we even had a theorem for it, right? Though I don't recall the name. Now, number 2. Alright, so we want to prove that every irreducible element is a prime element. Fine. Alright, we need to single out a single degenerate case, and that is when, well, okay. So, say that, consider some irreducible element B such that B divides A times B. Now, if P is equal to the identity, then the claim holds trivially. Because 1 is associated with every number, specifically then both AB and A and B, if we consider some B dividing A times B. Henceforth, P is not equal to the unit, to the identity. Now, we write, and because we are working on a unique factorization domain, we can, A is equal to some factorization of irreducible elements. So we have Pi again to say Ki. Oh, P1 to K1 times P2 to K2 times the dot times P n to Kn, and B is equal to P1 to L1 times P2 to L2, etc. all the way to Pn Ln. We use the same trick as we used in the first section. That is, if A has some element there that if A does not share a factor, say P6 with B2, then that's okay. We just write it in the factorization with the 0 exponent, right? So it's safe, it's fine. In this notation, we have that A times B is equal to P1 to K1 plus L1 times P2 to K1 plus L2 times times Pn to Kn plus Ln, and for I, we have that Ki plus Li are not equal to 0. Now, since P divides AB, there must exist at least one index j such that P divides some j such that Pj to Kj plus Lj divides P. but P is an irreducible element. This means that, this also means, by the way, that this could be interpreted as Pj to Kj plus Lj being in the factorization of P. But this means, since P is irreducible, that P is associated with Pj to Kj plus Lj. Pardon me, I had gone mad. Of course, it's just that Pj divides P, and then P is associated with Pj, because P itself is irreducible, and so is Pj, so they must be associate. It follows then that, P either divides A if Ki is greater than 0, or P divides B if Ki is greater than 0, or both, but at least one, which is precisely what we wanted, so hence P is prime. And finally, number 3, we shall essentially use precisely the same argument as I had given before. We will define a new function nu of some operating on the underlying set of the unique factorization theorem, and it will assign each one some natural number, possibly 0, and we define it as follows. So we say that nu of A, where A is equal, A has the following decomposition. So we consider again P1 to K1. P1, K1 times P2 to K2, etc., all the way to Pn to Kn. And we put this function equal then to the sum of the exponents. If A is invertible, so if A is invertible, I think it's also called if A is a unit, then nu of A is 0. Now, we know that the factorizations are unique up to associatedness. So nu A is well defined and will output an integer regardless of the factorization used. Now, by the previous theorem, we know that what did we use? A's. Okay, that AI plus 1 divides AI if and only if, or rather if nu of, so this strange norm we defined, of AI plus 1 is smaller than the norm of AI. Thus, the sequence of AIs cannot be infinite. As we would obtain a sequence, a decreasing sequence of non-negative integers. An infinite decreasing sequence, which is of course impossible, and this concludes the proof.